Hi, my name is Tun Lee Ng. I'm a statistics PhD candidate at the University of Wisconsin-Madison. I'm happy to give a talk about random weighting in LASSO regression. Our work has a Bayesian motivation. Suppose we have n data points and we have a parametric model. Uh, Using a Bayesian approach, we would like to know the posterior density of beta given y. As an example, suppose we consider this posterior density, whereby it has a Gaussian likelihood and a double exponential prior. Now, what we can do is to deploy MCMC based on the Bayesian LASSO model as introduced by Park and Kassala in their 2008 JASA paper to draw B posterior samples from this posterior density. And we get B MCMC samples here. Now, MCMC generally works well for moderate size model, but it becomes more computationally intensive and its mixing becomes hard to verify for larger models. Currently, there are many other methods out there to approximate MCMC, and one option is the weighted bootstrap or the random weighting approach that I'm going to introduce now. Suppose we take the negative log posterior density as before. We're going to draw independent random weights from a distribution with finite support and with a positive support and finite fork moments. And we're going to assign these weights on this objective function and optimize it to get one set of solutions. We call this one approximate posterior draw. So we're going to repeat the procedure from before, draw another set of random weights, and then assign it on this objective function, and then optimize it to get another set of solutions. So now we have two so-called random weighting samples. Repeat this procedure B times, and then we get these B random weighting samples here. So what we want to do now is to compare and see how these B random weighting samples here fare as compared to the MCMC samples that we have from before. And we test it on the much studied diabetes dataset. As you can see, the marginal posterior density of the MCMC samples and the density and the marginal posterior density of the or the kernel density of the random weighting samples overlap each other, and they are very close to each other. So we may ask ourselves, are there actually any nice statistical properties that's driving this similarity between the MCMC samples and the random weighting samples that we observe in the diabetes dataset? And for the random weighting samples, we are going to consider three different weighting schemes, namely RW1, 2, and 3, where the first scheme is that we don't assign any weights on the penalty terms, we only assign weights on the likelihood terms. And the second scheme is that we're going to have a common penalty weights here for all the penalty terms. And then for the third weighting scheme, each penalty term gets its own random weights. Now, here's the model setup. Of course, we're considering a linear regression model, but then we only require finite fork moment assumption for the error terms. We don't require normality assumption here. All predictors X are bounded, and then the rest are just common regularity assumptions that you find in the linear regression literature. So here's our main result. The first result concerns conditional model selection consistency, which is a property that the Bayesians are interested in because we want to know if the posterior distribution of our Bayesian model actually congregates at a true set of variables. And in this case, we prove that our random weighting samples actually do have this nice property. Specifically, if we assume the strong irrepresentable condition as propagated by the newspaper in 2006, JMLR, this condition here basically dictates that the irrelevant variables cannot be too correlated with the relevant variables. So with this condition, then with the appropriate rates of growth for the regularization lambda n, and with proper rates of growth for the dimension Bn, then the random weighting samples here do have the conditional model selection consistency. One thing we want to point out here is that for weighting scheme 3, whereby we assign different random weights for each penalty term, we require a more restrictive assumption here, whereby the irrelevant predictors must be uncorrelated with the relevant predictors. the statement of result here actually concerns with the conditional probability of the random weighting samples achieving the same sign or getting the sign consistency with the true model. But of course, this is a more restrictive case, and it covers the conditional model selection consistency that we are interested in. Now, another result is the asymptotic normality. Suppose now the Pn here is fixed, it's fixed dimensional, and that we're considering a non-sparse case. Then if lambda n grows slower than the square root of n, then we're going to have the random weighting samples here is going to get similar Bernstein von Mises results for the non-sparse fixed P-Bayesian linear model case. Now, from this theorem 3.3, you can see that there are two conflicting requirements if we compare that with theorem 3.1. In theorem 3.1, we deal with the sparse case, right? But here in theorem 3.3, we deal with the non-sparse case. And then in theorem 3.1, we require the lambda n to grow at a rate of n to the power c, where c is actually somewhere between half and 1, as we have stated in here. However, in theorem 3.3, we actually require lambda n to grow slower than square root of n. Now, so for a specific lambda n, you can either get conditional model selection consistency or asymptotic normality, right? You can't have one or the other, but not both. Now we ask ourselves, can we actually do something to get the best of both worlds? As in, can we get the random weighting samples whereby its conditional distribution congregates at the true set of variables as sample size increases, and that for the true set of variables, the random weighting samples actually do have asymptotic normality? Now, here's our main idea. We propose to use a two-step procedure in each of the approximate posterior draws. So what we're going to do is that in step 1, we're going to draw random weights, assign it on the objective function, optimize it to get to select variables. And then in step 2, for those selected variables from step 1, we will perform weighted least squares to estimate them. So then we're going to repeat this step 1 and step 2 for b times, and we get our random weighting samples. Now, if we do this, then I prove that in this case, we're going to have the best of both worlds. So not only these two-step random weighting samples here, the conditional distribution is congregating at the true set of variables as sample size increases, and that if you look at those true set of variables, the random weighting these two-step random weighting samples here, with proper centering, is behaving asymptotically normal. The centering here is actually an unweighted two-step lasso and least square estimator, whereby it is a lasso and variable selection followed by a least square estimation for the selected variables. So to illustrate our results, we're going to consider some simulation results comparing the 3 random weighting schemes that we talked about before with MCMC and the standard lasso residual bootstrap that Keith and I talk about in the Annals of Stats 2000 paper. Without going too much into details about the simulation schemes, what we do is that we consider 8 simulation settings, and the settings are listed here. In each setting, we will simulate 500 datasets. For each dataset, we perform MCMC and the other 4 methods. And then we compare the total variation distance between the eCDF, the empirical CDF of MCMC samples, and the empirical CDF of the samples from the alternative methods. Now, ideally, we want all the 4 methods to be as similar, as close to MCMC as possible. So we want the box plots to be close to 0 because we want the total variation distance to be close to 0 as possible. As we can see here, across all 8 simulation settings, the first random weighting scheme is actually having the smallest total variation distance when it's compared to the eCDF of MCMC samples. And except for settings 5 and 6, we can see that residual bootstrap usually have the largest total variation distance in this case. Now, random weighting scheme 3 performs the worst in the settings where the strong irrepresentability condition is violated. And then in another simulation setting here, we are comparing the sampling distribution of the conditional probabilities of selecting the first variable and the seventh variable among the 500 simulated datasets. Now, for the first variable, its true value is actually 1. So we want all the methods to actually select this variable, right? Because this variable is relevant. And as we can see here, all the methods here, except for the third weighting schemes in settings 5 and 6, all the methods here usually have very high probability of selecting variable 1. But if we look at variables, the seventh variable, whereby its true value is actually 0, then ideally we want all the methods to discard this variable. So we want all the box plots to be as close to 0 as possible. In this case, we can see that usually the first random weighting scheme and the MCMC have the smallest probability of selecting variable 7. And in some cases, for example, in settings 3 and 4 with the non-normal error term, the first weighting scheme is outperforming MCMC. And the same can be said for settings 7 and 8, where it has larger dimension. Now, in all cases here, we can see that the standard residual bootstrap is having some of the largest probability of selecting variable 7, which is undesirable. So this sums up for my presentation, and I'm thankful for your time and attention to listen to my presentation.